Now, let's predict the electrolysis of the following electrolytes using the inert electrodes. So the first one is the molten salt. The electrolysis of the molten salt requires a very high temperature. This is because we are going to melt the ionic salt so that we can get it into the liquid form. So there's only two species present in the molten sodium chloride salt. The species are the sodium ion and the chloride ion. So chloride ion will attracted to the anode and sodium ion will attracted to the cathode. So since we only have two species present, so chloride will be discharged at anode and sodium will be discharged at cathode. So the half-cell equation are written as follows. From the half-cell equation, we can see that the chloride ion undergoes oxidation and form the chlorine gas. So since chlorine gas form at anode, we can see gas bubble evolve at anode electrode. And at cathode, the sodium metal is formed at cathode, so we can see a shiny metal deposited at our cathode electrode. So the product formed at cathode is the sodium metal. In the electrolysis of water, since water is an electroactive substance, it may undergo oxidation or reduction process. When water undergoes oxidation, it will release an oxygen gas and produce the hydrogen ion, while when water undergoes reduction, it will release a hydrogen gas and produce an hydroxide ion. So on our anode and cathode, we can see a gas bubble evolve. The product formed at anode and cathode are oxygen gas and hydrogen gas respectively. Next, let's have a look at the concentrated aqueous sodium chloride. The species present in the concentrated aqueous sodium chloride are sodium ion, chloride ion, and water. So during electrolysis, the sodium chloride and water are attracted to cathode. Since the inert water is more positive than the inert of sodium, water is easier to be reduced. So at cathode, water is being discharged. So water undergoes reduction by releasing hydrogen gas and hydroxide ion. While at anode, chloride ion and water are attracted to anode. In the concentrated solution, chloride ion will be oxidized because of its high concentration, even though the inert value of water at anode is more negative than chloride. But in dilute aqueous sodium chloride, at anode, water will be selected for oxidation because it has more negative inert value. So, at anode and cathode, both water will be oxidized and reduced in the dilute aqueous solution of the sodium chloride. For the aqueous sodium sulfate, by using inert electrode, the species present in this electrolyte are sodium ion, sulfate ion, and water. So cathode will attract sodium ion and water. Since the inert water is more positive than inert sodium, water will be reduced at cathode, while anode will attract the sulfate ion and water. So since sulfate ion will not be oxidized because it is also an ion, so water will be oxidized at anode. For the aqueous solution of copper sulfate by using an active electrode, which is the copper electrodes, cathode will attract the copper 2 plus ion and water. Since copper 2 plus is more positive than inert of water, copper 2 plus is easier to be reduced at cathode, while at anode, sulfate ion and water will attract at anode. Since the sulfate ion will not be oxidized because it is also an ion, and inert water is more positive than inert copper, so copper will be oxidized at anode. So this method is used for purification of metal. Copper is transferred from anode to cathode through the solution as the copper 2 plus ion. The concentration of the copper sulfate remains unchanged. There are many other uses of electrolysis. One of them is the electro-refining of copper. The item to be refined is anode. The impure metal of copper is used as the anode and the refined metal will be deposited at cathode. Another uses is the electroplating. The item to be plated is the cathode in the electrolytic cell. In electroplating, the less expensive metal will be put at the cathode and then more expensive metal will be put at anode. So the less expensive metal will be plated by the more expensive metal. The electroplating also used for decorative purposes or to protect metal from corrosion. Faraday's first law described the relationship between the amount of electricity passed through an electrolytic cell and the amount of substance produced at each electrode. So the Faraday's first law states that the mass of an element liberated on an electrode during electrolysis is directly proportional to the quantity of the electrical charge which passed through the solution of an electrolyte. In 1 mole of electron, there is 1 Faraday and 96,500 coulomb. So this is what we call Faraday constant. Let's have a look at an example to solve the problems relating to the Faraday law. In example 1, we have an aqueous solution of copper sulfate electrolyzed using a current 0.150 ampere for 5 hours. The question asks us to calculate the mass of copper deposited at cathode. So since the aqueous solution of the copper sulfate consists of 3 species, which is copper 2 plus, sulfate ion, and water, at cathode, we know that copper 2 plus and water is attracted to cathode, but copper 2 plus will be discharged at cathode since it have more positive inert value. So in this question, already mentioned that copper deposited at cathode, so it does help us to determine which one will be discharged at cathode. So at cathode, copper 2 plus ion will be reduced to copper solid. Okay, so by doing so, copper 2 plus will gain 2 moles of electrons. Okay, so since here we have positive 2 charge, okay, here we have 0 charge, so we need 2 electrons to give us negative 2 charge so that each both side of our half cell reaction got same charge. So from this half cell equation, we can see that every 1 moles of copper is equivalent with 2 moles of electron. 2 moles of electron equivalent with 2 Faraday. 2 Faraday equivalent with 2 times 96500 coulomb. So since we have the current and also time, don't forget to change the time in second, we can calculate the value of Q, which is the quantity of charge used in this electrolysis. So the quantity charge that is used in this electrolysis is 2700 coulomb. So since we need the mass of copper, so we need to know the number of mole of copper. Alright, so from the stoichiometry, from the relationship that we got here, alright, so take out the moles and charge since we have the quantity of charge used in this electrolysis to find the number of copper deposited at cathode. So by using the conversion factor, so we have 2700 coulomb times with, okay, so we don't need the coulomb here, okay, so the coulomb here will be put at the bottom and we need the moles, so we are going to put moles at the top. Alright, so the number of mole of copper deposited at cathode is 0.01399 mole. And find the mass of copper deposited. Okay, so 1 moles of copper is equivalent with 63.5 gram. So use the conversion factor, we will get the mass of copper deposited at cathode, which is 0.888 gram. The second example, so we have 0.86 gram of chromium, okay, from an electrolytic bath containing the chromium sulfate aqueous, okay. 2.5 minutes is allowed for the plating. How much current is needed? So the question asks us to find out how much of current is needed in this electrolysis. So since we have the aqueous solution of the chromium sulfate, okay, so there are three species present, okay, as usual. Okay, so the chromium is the chromium 3 plus ion, and then we have sulfate ion and also water. Since chromium is deposited at cathode, okay, the half cell equation at cathode is written as chromium 3 plus ion, okay, produce, or chromium 3 plus ion is being reduced to chromium solid. Okay, so to balance the equation, chromium will gain 3 moles of electron. So 1 moles of chromium is equivalent with 3 moles of electron, equivalent with 3 Faraday, equivalent with 3 times 96500 coulomb. To find the current needed, we need the quantity of the charge. Okay, so since we have the mass of chromium here, find the number of mole of chromium, right? So 0.86 gram of chromium times with 1 mole divided by 52.00 gram. Okay, so since in 1 mole of chromium, it has a 52 gram of mass. Okay, so the number of mole of the chromium deposited at cathode is 0.0165 mole. So since we need the quantity of charge, okay, so we have the moles here. So take out the moles and charge, okay, from our relationship here. Okay, so 0.0165 mole of chromium, okay, multiply by 3 times 96500 coulomb, since we need the charge, and then we don't need the mole, so we are going to put the mole at the bottom. Okay, so we will get the quantity of charge used in this electrolysis to produce 0.86 gram of chromium is 4776.8 coulomb. So by using the formula Q is equals to IT, we already got our Q, right? So substitute the value, okay, equals to I times with time. So the time here 2.5 minutes. Don't forget to change it into seconds, right? So we will get the current needed equals to 31.8 ampere. Okay, so I think there's a problem with this question. Supposedly this one should be 12.5 minutes. Okay, terlalu singkat ni masa ni. But it's okay, that's how you do it. The last example, we got a molten magnesium chloride. Okay, so assuming 35.6 gram of magnesium metal form. So how many moles of electrons are required? How many coulombs are required? How many amperes are required to produce this amount in 2.5 hours? So in molten magnesium chloride, there's only 2 ions present, which is magnesium ion and chloride ion. So since we have the mass of the magnesium metal form, so we are going to focus on cathode. Okay, so we have cathode reduction process, right? Magnesium ion will be reduced to the magnesium metal, okay, by gaining 2 electrons. So every 1 moles of magnesium equivalence with 2 moles of electrons, equivalence with 2 Faraday, equivalence with 2 times 96500 coulomb. So since we need the moles of electron, so we are going to take out the mole of magnesium and moles of electrons since we have the mass of magnesium here. So find the number of mole of magnesium deposited. Right, so 35.6 gram of magnesium times with 1 mole divided by 24.3 gram of magnesium. Right, so the moles of magnesium deposited 1.465 mole. So 1.465 mole of magnesium. Okay, so use the conversion factor. So we have 1 moles of magnesium here. We don't need the mole of magnesium. We need the moles of electron. So put the 2 moles of electron at the top and 1 moles of magnesium at the bottom. Alright, so we will get the moles of electron used in this electrolysis is 2.93 moles electron. For the second question, we need to find how many coulombs are required for this electrolysis. So take out the mole of magnesium and the coulomb here. Okay, so since we have the moles of magnesium, alright, so we use the conversion factor again, 1.465 moles of magnesium times with, we don't need the mole of magnesium, so put it at the bottom, right? So 2 times 9650 coulomb at the top. So now we will get the coulombs required in this electrolysis, which is 2.83 times 10 to the power of 5 coulomb. And for the last question, how many amperes are required? So use Q is equals to IT. So since we have our Q, 2.83 times 10 to the power of 5 coulomb equals to I times with the time taken, change it into seconds, okay, times 60 times 60, right? So the ampere required in this electrolysis is 31.4 ampere.